Our final talk for today is Avionics System of Systems Simulation and Modeling Toolchain by Juan Gutierrez and Dhruv Monga. Juan is a Vice President for Business Development and Airborne Systems at Physical Optics Corporation. And Dhruv is a machine learning research engineer at Physical Optics Corporations in the Information Sciences Software Group. Here's Juan and Dhruv with their talk.
Hi, thank you, Shane. So as Shane mentioned, me and Juan will be presenting the Avionics System of Systems Simulation and Modeling Toolchain, otherwise known as ASSIST. Juan will be giving some background on our company. So Juan, take it away.
All right, thank you, Dhruv, and thank you for bringing up the slides. So Physical Optics Corporation. So some of you probably know us. We've done a couple of items with the Army so far, and in the AADL realm. We have been following AADL and promoting our ASSIST program for the last several months, almost probably about a year and a half now. But looking at the company background, we were just acquired as a small business from Mercury Systems. And now we are going to become Mission Torrents under Mercury Systems. But from a POC side as a business unit, we were founded back in 1985 as a small woman-owned company that transitioned over to an employee-owned company that has now transitioned over to Mercury Systems. And that just happened this past month. We have been financially strong over the years, looking at about 126 million last year and looking at over 150 just for this business unit alone coming up in 2021. We have over 300 employees here in the Torrance facility, with 27 of them being PhDs and 156 engineers. So we really like to say that we have a large amount of research and development expertise that actually happens out here in Torrance. We have 6 buildings out here in Torrance that encompass 170,000 square feet. We just did a 27,000 square foot expansion in 2020 that actually helped out with our manufacturing and our research and development laboratories. 160 patents over our lifetime of the business. And we do have a strategic advisory board that we use that have outside and independent influence coming in so that way we can gauge the market and we can look at to see what technologies that we are actually pursuing will actually make it over into production. One of the things that we have been very proud of here at Physical Optics Corporation is the fact that we are AS 9100, 9110, and a CMMI level 3 development house, software development house. Also recently in the past 18 months, we've been accredited as an independent testing laboratory. We are one of only 6 companies, large or small, in the US that actually have all these certifications. So that is something that we really like to push forward as far as reducing the risk to program managers and other programs, and the fact that we have the established processes and the ways to oversee programs on a large and small scale. Dhruv, if you can go to the next slide. So we at POC, we have several areas of focus. Right there at the top center, you're going to see AMCS. AMCS is one of our flagship programs that fall under the Jarvis Mission Computer Program. Jarvis stands for Joint Avionics Reconfigurable Virtual Information System. And that is our distributed mission computer. And we're doing a development program with the NAVAIR V22 program office to establish that distributed mission computing into that platform. From that, we're looking at AMCS, which is the Army version of an independent distributed mission computing and MOSA established product as well, the Aviation Mission Common Server. Throughout today, there have been questions and some comments as far as how AMCS will actually dovetail into the mindset of what the Army Aviation Enterprise is looking at for MOSA, FACE, and some of these standardization programs that move forward not only into FVL, but also into the enduring fleet. So that is really a large area of focus for us here at POC, as we are one of the 3 vendors that are moving forward under that program. What you'll also see is that we have a large and in-depth experience with RF and EW. We're diving into AI and deep learning. We have an extensive experience with cybersecurity, so much so that one of our only programs that we've done here outside of government funding and entirely internally funded is coming up with our own encryptor for a data at rest solution. on the bottom left, that's what you'll see under the cybersecurity moniker. Pushing that forward, we believe that we are at the forefront of what cybersecurity requirements are in the data at rest realm, as far as pushing over into data in transit. We have a breadth of experience in sensors and scanners, looking at radar and LiDAR and even X-ray technology for non-destructive inspections. And then emergent technologies such as our ORFOM project, which is a fiber optic cable draw that is actually done up at the International Space Station to reduce the number of impurities that go into a fiber optic cable and actually increase the bandwidth of that cable from 4 to 10 times. Our DREAM program right now is an Army-funded program, developmental program, I should say, that is a smart expendable looking at an RF energy and returning that back to the threat in a small form factor that doesn't need or does not require any changes to the current enduring fleet systems of expendables. And then we have the Argus program, which is unmanned surveillance, looking at some of the sensors and doing a sensor fusion in coordination with that. So as you can see, POC does a lot of work here, but we're trying to tie it all into what is coming up with the enduring fleet and the future vertical fleet in moving forward with some of these MOSA efforts and moving that into software. Dhruv, take it away.
Great. Thank you, Juan, for that great overview. So I'm going to start covering the ASSIST project. To begin with, I'm going to start covering some of the challenges that we're hoping to address with ASSIST. The first challenge is addressing the increasing complexity of avionics systems. So over time, there's been an exponential growth in the number of source code lines in avionics systems. And what this higher complexity really means is that there are higher development costs and also higher costs for validation and verification for avionics software. The second main challenge that we're hoping to address is the difficulty in using multi-core processors in avionics. Currently, it is difficult to use multi-core processors because it is difficult to verify and guarantee their performance during the requirements, design, and implementation stages. Additionally, shared resources within multi-core processors make validation and verification difficult and also costly. ASSIST really hopes to reduce some of these development costs associated with these challenges in the avionics industry. So ASSIST solution really targets the design phase of a project lifecycle. The goal of ASSIST is to detect defects in the design that may be created during the ConOps, requirements, and design phases. So in this figure, if you can focus in on the top row, for the ConOps, any design flaws that are introduced in the ConOps stage, the later they're left unaddressed, the more expensive they become to fix. Our goal is to detect any of the design phases that are created in the ConOps, requirements, and design phases in the design phase so that they're not as expensive to fix and they can be much more easily corrected. So this figure highlights the overall general ASSIST approach. ASSIST takes as an input the system architecture and design implemented in AADL. From this design, it creates a system of systems models that are then simulated. ASSIST drives the simulation through simulating data inputs, and then it tracks the flow of data through the system, first through simulating the data transferring between components through data buses. And this includes tracking message transfer times and bandwidth utilization. And then ASSIST tracks the data processing done by each component and simulates it. So it can track the operation of, for example, CPUs, memories, and threads as a processing data. From this, it compares the actual observed data processing to the requirements set in AADL to determine any defects that may occur in the system design. It uses these detected defects to recommend corrections, which can then be translated back into AADL for an iterative design improvement. So to illustrate this, take as an example a system consisting of input data flowing into the system via a buffer, which then sends the data to processors, which execute threads, which then require access to shared resources like the memory and the bus. Shown in red are potential design defects that may occur during the execution of this program. So for example, if the buffer exhibits an overflow that may cause an execution time violation in the processor because these components are all mutually coupled and interconnected. So when processors exhibit execution time violations, threads may then exhibit contention and race conditions, which may then cascade down to lack of resources in the memory or delays and latencies in the bus. Assist is designed to detect and correct these kinds of defects that are caused due to the mutual coupling between all the components of a system. The assist capabilities are split into three primary groups. On the left side are the primary capabilities that have already been fully integrated into assist. This includes a baseline simulator that can simulate the components and subcomponents of an avionics system. In the middle column, which is currently being integrated into assist right now, is the unified error and behavioral analysis capabilities. These use the AADL annexes to identify indirect error propagations and analysis, as well as provide evaluation of system resiliency and fail-safe conditions. In the third column, in its final version, assist will also include change impact and what-if analysis capabilities. These capabilities allow evaluation of multiple system configurations while also being able to identify ripple effects in system design caused by system architecture changes. This slide presents a high-level overview of the assist architecture. There are three main components to the architecture. One is the user interface, which is accomplished by developing assist as a plugin to the OSATE AADL development environment. The second section is the core AADL simulation engine that is the heart of assist. This simulation engine has actually been designed to be compatible with the cloud, meaning it can be deployed on any number of cloud-hosted services. What this does is it allows assist to simulate much more complex systems by harnessing the more powerful machines available on the cloud. Additionally, assist can evaluate multiple system designs in parallel by harnessing multiple machines on the cloud and compare them directly. Finally, assist leverages a time series database. This low latency database can be deployed on the web as well and provides built-in analysis and visualization capabilities that can be accessed directly from the OSATE plugin. This presents a high-level overview of how assist will be integrated with OSATE. Highlighted in green are the features specific to assist. Mainly, the most important features are users will be able to organize and manage their simulations and deploy them based off of AADL they have written using OSATE's AADL editing capabilities. And then also view simulation data and real-time analysis right within the OSATE environment. All of OSATE's capabilities will be able to be leveraged to edit AADL, to view project dependencies, manage projects, and also view AADL system designs as well. More specific to assist, built into the OSATE environment will be an ability to open a data dashboard, which is able to access the simulation data created by assist simulations directly. Importantly, users will be able to create custom queries to do custom analysis on any simulation that is collected, on any simulation data that is collected, while also being able to compare simulation data between different components and also even between different simulations. This slide shows some of the statistics that assist is able to collect and visualize. For each of these graphs, on the x-axis is the time for the simulation, shown approximately is about 15 seconds, 20 seconds. And then on the y-axis is the value for the statistic, which changes per graph. So for example, on the top left corner, shown is the CPU utilization per core that was collected during the simulation. Some other statistics that are collected are the cache hit and miss rate, the processor assigned to each thread while it's executing, how long each thread takes to execute, and some others. I'd like to bring your attention to the top right graph. Assist during simulation compares the amount of time spent executing for each thread versus the deadlines that are specified in the AADL specifications for that system. Anytime the collected statistics for the thread execution time exceeds the deadline for that thread, a deadline violation is logged. Users will be able to drag around the deadline violation and zoom in to the time area of interest. All the other graphs will actually update to that time area of interest as well, so users can view the system state as a whole in order to troubleshoot any violations that are detected. So I'm going to quickly cover some of the use cases for Assist. To drive the use cases, we created a sample system consisting of a flight data recorder, which has a data bus, mission computer, and display system. As an input, we played back real-life flight data that was recorded during an actual flight. And to stress test the system, we plugged in a hardware-in-the-loop video camera. We tested the system under two configurations, one with a dual-core CPU and another with a quad-core CPU. This slide details some of the statistics that were collected, and this was motivated by a study done by the FAA on the assurance of multi-core processors in airborne systems. This shows some of the results that we collected from this scenario. In the top row shown are the CPU load percentages. On the left is the dual core. And for the dual core, on average, there was relatively high CPU loads, whereas for the quad core, we noticed a significant reduction in the CPU loads in all processors except for one, indicating additional headroom was available. In the middle shows latency incurred by resource contention and unavailability of resources. For the dual core, there was a significant amount of latency incurred by that, whereas for the quad core, there was almost none. Finally, in the bottom row are the deadline violations we observed for all the threads. For the dual core case, we observed deadline violations in many critical threads, likely caused by insufficient resources. For the quad core, we only noticed deadline violations for the video process thread, but not for any of the other critical threads, meaning that additional sensors, assuming that they didn't have too high of a data rate, could also be added to the system. I'm going to highlight some of the other capabilities that Assist will have when it's completed. One is the what if analysis. Users will be able to generate multiple variations of a baseline system by altering, for example, the number of cores available, the size of the RAMs, and even scheduling algorithms. Users can then specify design criteria, such as optimizing for minimizing processing time for certain tasks or maximizing CPU utilization. Assist can use the cloud capabilities that it has to simulate all system design variations in parallel and then rank them in terms of how well they meet the design criteria specified by the user. Assist will also contain error and behavior analysis, which use the error and behavioral annex to define error propagation paths and behavioral requirements for each component. During simulation, Assist will intentionally inject component failures into the system to evaluate how resilient the system is in fail-safe conditions. And it will also identify indirect failure propagations resulting from the interaction of the error annex and the behavior annex. Finally, Assist will also include security analysis capabilities. For this, a given system is defined as nodes and edges, where nodes are components in the system and edges are the relationships between the components. The relationships can be subcomponents, data flows, or connections. Users can then assign security classifications to each component, either secured or unsecured, and Assist can, using graph algorithms, identify vulnerabilities in the system where secured components are compromised due to connections to unsecured components. And that is the end of the presentation, opening up to questions now.
Thank you very much, Juan and Dhruv. There's a very interesting capability that you have provided here. And looks like there's a lot of potential applicability to systems that have already been designed with AADL. So do you have, I think Juan stated that there would be a transition into future vertical lift in the future. Is there like a game plan for how that would work? And do you know when it might be available?
So what we're looking at doing is instituting Assist as a tool for industry to use for their capabilities and to see how it actually fits into the larger system. So once Assist has been modeled in the AADL language, our thought is that once we give this to industry, they can use this as a tool to see how on a subsystem level it affects their systems, but also on a macro level for the platform, it might be able to identify how certain capabilities from different industry partners actually conflict with each other and run into issues as they look into pulling at the same resources at the same time. So what this will be able to do for the Army Aviation Enterprise as well as industry is be able to work that out and be able to see those issues early and be able to fix them early on, just like what Dhruv said, in a less costly fashion.
So is the plan to sell like a license to an industry partner to use the Assist tool? If they, how would that, can you explain that a little bit?
So right now we're looking at the different options that are actually given for that type of capability. We have discussed licenses. We have discussed just sending this over. We have discussed with other entities in the Army to maybe supply this as GFE to certain customers or to certain vendors, so that way they can use it prior to what they're looking at. So there are several different options that we're looking at right now, and we're trying to figure out the best one.
And then I guess if there was, I guess there are issues potentially with proprietary data if you were going across a supply chain.
Yes, for sure. So there is a problem with that. And we're looking at the differences of if you did have proprietary data and we were able to maybe put this on a cloud, is to have certain users be able to have certain functionalities, maybe the Army being at the top tier and POC being at a lower tier and not seeing all that informational data, but to have vendors actually go into the cloud, input their capability into that system, and then be able to run it with all the other vendors that are looking to actually add capability to that platform. Again, we're still kind of working out the details of how that's actually going to be implemented and to see whether or not the security functionality is going to be capable of actually executing that plan.
Sounds very interesting. I think we have, I think we've finished with the questions that I'm aware of. So I want to thank you both for this very informative talk. And I believe that was you were the last talk of the day. So that's always a good thing. Although you're in California, so you still have plenty of time left in your day. And,
Yes.
And I'd like at this point to turn things over to Jerome for concluding remarks for today. Thank you again.
All right, thank you. Appreciate it.
So much.
Thank you all, and thanks Fred for the intro. So as you said, it is now time to close the first day of the third edition of this AADL ACVIP User Days. And first, let me thank the audience and all the speakers for the excellent talks and Q&A sessions. Let me wrap up a little bit of what have been discussed today. So first, in his keynote, Pat Mason insisted on the importance of architecture in support of system operations and how software is shaping future capabilities. This led to a new definition of the role of software and architecture. This is impacting not just engineering as we know it, but also the whole acquisition process from early system definition, its engineering, its V&V and deployment. Then Alex Boyston introduced in more detail AADL and ACVIP, the past and current effort to raise the maturity of AADL as an open standard and ACVIP as a process to apply it. This effort spans over a large community, and the other talks were there to introduce a portion of this community. First, Sam Proctor from the SEI introduced our effort in supporting DoD and its contractors in using AADL and ACVIP, and he has illustrated the wide variety of topics AADL and ACVIP can provide solutions for. Then, a couple of tool vendors like Garrett Thurston from Dassault presented the scope of ACVIP and MBS in general, and the many conceptual layers that build a complete system design. He emphasized on the importance to properly weave system views. Then we got 3 talks on systems modeling and verification. Roshan Thomas from MITRE provided one particular instance in combining system views through the SCAPS project, combining AADL, Simulink, and simulation to assess models. Sean Klein from IDT showed how to leverage MBSE techniques, again, SysML and AADL, to automate test and retest of systems. And finally, Prachee, Sharma, Dhruv, Monga, and Juan Gutierrez introduced their own approach for Avionics simulation and modeling, with a strong emphasis on multi-core systems. All these talks illustrate the wide variety of topics that AADL and ACVIP are addressing. Those talks will be available through the SCI Digital Library in a couple of weeks. Let me also remind you that you will receive an email tomorrow morning with all the details to connect to our Day 2 sessions. Again, thanks to all our speakers and audience, and see you tomorrow.